Okay, so for the first part, we'll be revising through just general concepts in EEE. And in this case, we've got this basic question. It was worth an entire 14 marks. So this was a giveaway. So what they're asking here is that for the circuit shown in the figure, so we've got that figure below, they want us to find the equivalent resistance, REQ. And then apart from that, they also want us to find the conductance, GEQ. And then we also have the value of IO there. So let's go through how we're supposed to get this. So we know to say when getting the equivalent resistance, all we're looking for is if two resistors are in series, then we have to add them. If two resistors are parallel to each other, then their combination is going to be the product of the two, and then the sum divided by the sum of their resistance. This is how we combine two resistors in parallel. And if they're in series, we just add them like that. But of course, the more general description of this, and that will be required when you're trying to combine three resistors in parallel at the same time, it will be their combination R total will be equals to 1 over the first one, plus 1 over the second one, plus 1 over the third one. And if you've got more, of course, it continues. But mostly when you're performing these evaluations, we tend to prefer to do them in pairs, meaning combine the two in parallel, then combine them with the third they're in parallel with. So usually this is how we approach them. Okay, so with that in mind, let's see how we were supposed to work out this. Of course, there are other methods that we use when it comes to breaking down these circuits, like this, the star delta transformations. But I think for this one, we actually did not need the star delta transformations. But where do we start from here? Well, you want to start as far from where you're observing the circuit as possible. In this case, the circuit is being observed from this part here, according to where they've indicated the RIQ there. So observing the circuit from this side. So this is where we're viewing the circuit from. Trying to combine everything that is this side into just one whole resistor. How do we do that? Well, we want to start from this side. So what do we see that? You can start from anywhere really, but in most cases, we start from the furthest. That's where we find resistors which can easily combine. Well, by observation, what you have to keep in mind is that these 2 points, or this is basically just one node. So this whole line here, this is technically just one node. What do I mean just one node? It means that it's as if you have 1 point here, then to that point, you have the 12 ohms on top connected, the 12 ohm resistor, and then you have the 6 ohms also connected to that same point. Then you've got the 80 ohms also connected. Then you've got the 20 ohms also connected. My point is this, even though we see this line between the 2 points, the whole thing here is actually taken as one node. Why is it like that? Because a node is just seen as a point, a connection between two circuit elements. And in this case, when we say this, let's say, let me do that. When we say this is a connection between this circuit element and this circuit element, and this is also a connection between this circuit element and this circuit element, notice that these 2 points are then connected. So these 2 points, this one on top in blue and also this one here in blue, they are then connected and you don't see any circuit element between them. So because we don't see any circuit element between them, these 2 points, that whole blue line is technically just 1 point, but it's like 1 point that is just stretched apart. In the actual sense, that point can be different because of course the material also has some form of resistance. So it might vary what is happening between the 2 points. But generally, if we say the internal resistance is negligible, which would be the case in most cases, it implies that that whole point is just 1 point. What does that imply? Well, it then implies that the 80 ohms, this 80 ohms and this 20 ohms, on one side here, they are connected to the same point. Even this side, so these are connecting to the same node. So I'm literally saying this one here is practically just one node there. So the 20 ohms connects to this part of that node, and the 80 ohms connects to that part of the 18 of the same node. So in the end, when the 20 comes to connect this side and the 80 also comes to connect this side, which is also another node, so we see that the 20 ohms and the 80 ohms are actually connected in parallel. For two resistors to be in parallel with each other, it implies that they must be connected to the same two nodes at their respective ends. Meaning that in this case, we sort of say they are connected to that node. The other end, we've just seen that even though this is a straight line like this is also technically just the same node. So the 20 ohms down here, the 80 ohms on top there, the two are connected in parallel with one another because they stand at the same two nodes. The nodes being this one and this one here. So based on that, we can combine them. Their combination will be 80 because they are parallel by 20 divided by 80 plus 20. So what will be the answer here? Is it 116 with 2 zeros there and 100 here? Is it this? You guys can confirm this. Is it that? Are we see? Is it that? Yeah, great. So looks like we combine that to get a 16 ohms. What does that then imply? Well, most cases I'd want to redraw the circuit every step of the way, but you really want to see how much time you have and how many marks you have. But in this case, just make sure that we're able to keep track of what is happening. I'll keep creating a sketch of what is happening so that we can basically keep track here. So we have this one here, the 5 ohms there. And then we have the node that goes to connect to the 6 ohms. And then this comes to this end here. And then coming up, we have the 60 ohms on top. And then coming this side, we have the 12 ohms here. Okay, so 6 ohms here, 12 ohms here, 60 ohms here, 5 ohms here. Okay, what else are we seeing there? Okay, so this comes down. We have a power source. Okay, so this comes like this. I think we have a resistor here. Yep, 15 ohms. And then we have this. And this side, 20 ohms. Okay, so the 60 ohms goes down, this goes this side, and then the 60 ohms comes down like this. And then this side, we have this part. Is it? It's coming from the top. So it's coming from here. Then we have a resistor here. Then we have this. This is where we had that 60 ohms. Now, what we saw earlier was that the 20 ohms, basically this one and this one. Yeah?
That 80.
80, yeah, 80, sorry, 80, not that 60. 80 ohms here. Okay. So yeah, we have 80 and 20 ohms. So the two in blue there are in parallel, and we have seen what their parallel combination ends up giving us. So we saw that was just 16. So what then happens here is that our circuit can be redrawn. So let's just put what the voltage here is. So you have plus minus, that is 40 volts. Okay, so here we have 40 volts. So the parallel combination here has been reduced. So remove this, and in place of those, we're going to have, doesn't matter whether we connect it here or at the top or even somewhere on the middle, but all in all, this reduces to just 16 ohms. Now at this point, what else happens? Well, here we now have to see, first let me ask you guys this, these two, are they in parallel or not? The 15, they are not in parallel, because even though down here they connect to the same two nodes, the same node, here they connect to this node, here also this node, which is basically the same node here. On top, notice that this connects this side and this connects the other side. So this line on top is not one node because it has a circuit element between. So because of that, the 16 and the 15 here are not in parallel with one another. But however, these two here are in parallel with one another. Why? This is one node, this is one node, and they connect to the same two nodes there. So the 12 and the 16 are in parallel. Let's combine them. So we have 12 by 16. Is it 16? 6. So we have 12 and 6 divided by 12 plus 6. What do we get here?
Okay, you know what we think, like, I think you can imagine.
So we get 4. So when you combine those, we end up getting 4. So what this implies is this, we can remove this, and in place of it, we can put 4 ohms. Again, it doesn't matter where we put it. So in this case, I'll connect it here. So here we have 4 ohms. So that is done. Now it becomes quite obvious what happens. In this case, when we observe these two are now in series with one another. So the 4 and the 16 are now in series. We're just going to add them and we get 20. So in our new circuit, we're going to remove these, and in place of these, we're going to put 20. At this point again, the next part also becomes obvious. There are two things that you have to see. The 15 is in parallel with the 20, and together they are also in parallel with the 60 on top there. I hope you're able to see that. So you can combine them using that way of combining 3 resistors in parallel. But again, mostly we tend to prefer to work with them in pairs. What do I mean? I can start by saying that, okay, I'll treat these two to be in parallel. So I'll combine those as the 15 and the 20. So I'll say I have 15 by 20 over 15 plus 20. So if I do this, what will be the combination here?
60 over 7.
60 over 7? Okay, so that becomes the combination of those two. So I can easily now just remove these, and in place of them, I will have 60 over 7. Next up, we now see that the 60 over 7 is now in parallel with that 60 there. Why? They connect to the same two nodes there and here. So they are in parallel. We can combine them. So we now have 60 over 7 by 60 divided by 60 over 7 plus 60. What will be the solution here? 7.5 ohms. So in this case, it implies that our circuit now reduces even further. In place of all this, we're now just going to have 7.5 ohms. Now these two, obviously you can see that they are in series. So we can conclude that the total resistance or the equivalent resistance is just going to be at those. This is going to be, is it 12.5? We get 12.5. So the whole circuit now can be withdrawn. So that now all you have is 12.5. Okay, so we have found REQ. So that sorts out the first 8 marks. The next part, sorry. Yes, please.
A question on that same RE.
Go ahead.
For the, you see where the arrow is pointing?
Yes.
Does that mean that the resistance except the 5 ohms, or everything is accounted?
Everything.
Then what's the point of the arrow?
The arrow is basically telling you to say this side of the circuit. When you look at what is happening this side, first current passes through the 5, it goes through all this mess, and now it is coming back. So we're seeing the resistance from this point, viewing it backwards here. So we're looking at all the challenges encountered, if I would call it that. So looking at all the loads that have been encountered by current from that point going backwards. Notice that the 5 ohms has to be included. You get that? Yeah. Had the 5 ohms been somewhere here, then we can say that we are not including it here. Okay, so with that done, next part, we can now look at the conductance G. Well, the relationship between conductance and resistance is quite straightforward. If you know what the resistance is, getting the conductance, this is just going to be 1 over the resistance. So conductance is just the inverse of the resistance. Since we already have Req, the conductance will just be 1 over Req. So the total conductance Geq will be equal to 1 over Req. So this is why this only carried 3 marks, because you can just use what you're from finding to find what it is. Otherwise, if you wanted to complicate your life and saying that, okay, conductance for this is 1 over 80, conductance for this is 1 over 20, it would now take you even longer to find the same answer. But just seeing that it will also be governed by that behavior would simplify your life. So since we found the equivalent resistance as 12 over 5, then the equivalent conductance will just be 1 over that 12.5. And we know the units for conductance. You can write the ohm backwards, or you can just write the inverted symbol for conductance. We know for resistance, resistance is the ohm like that. So this is going to be the same thing, but just inverted. Okay, that sorts out number 2 for 3 marks. And then we now want to determine what I/O is. I/O is the current being supplied from the source. And we know to say, having figured out what the total resistance is, I/O becomes quite straightforward. I/O is the current coming from the source. So by Ohm's law, we know that voltage is equals to current times resistance. In this case, that current is the I/O. So I/O will be equals to voltage divided by the equivalent resistance. So the supplied voltage is 40 divided by the equivalent resistance, 7.5. It was 7.5, was it? No, 12.5. Why am I writing 7.5? 12.5. So this becomes our way of finding I/O. Again, another straightforward calculation. So for this, you were given all those marks. These were 3 marks, guys. I hope you were able to get them. That's 14 marks. Okay, so any questions on this? Okay, looks like we are okay here. We can move on to the next one. Okay, so for this one now, similar approach. They're asking for the equivalent resistance. Here they've given the equivalent resistance less marks. The next part, they want us to find the voltage Vx. And then after that, they want us to find the power absorbed by the 2 ohm resistor. Okay, so let's start Rq, the equivalent resistance. So how do we find the equivalent resistance? Well, just that. Again, we'll start from the furthest point, this side. Those two are in parallel. So we have 8 by 12, and then we have 8 plus 12. What is this giving us? What are you getting here? 3.8? Okay. 4.8. Okay. So if these two are giving us 4.8, then their combination is in series with the 1.2. So I'll basically just say plus 1.2. So it's 4.8 plus 1.2. So this becomes, is it 6? So I think that becomes 6. So to just give you an idea of how the circuit now looks like, we now have the current source this side. We have the resistor here. And then we have the resistor here. The resistor there. And then we have this resistor. And also that resistor. 1 ohm, 4 ohms, 6 ohms, 3 ohms, 2 ohms, and 6 amps. So we have just combined all these here, and we've seen that these ended up giving us 6 ohms. So we'll just copy this. And now I am saying that everything which was here reduced to just 6 ohms. Then let's pick it up from here. So you see that the 6 ohms currently is not really doing anything, but look at these two here. Let me highlight them. So look at these, the 3 ohms here and the 6 ohms here. The two are in parallel and they can be combined. So here we're going to have 6 by 3 over 6 plus 3. Then just like before, their parallel combination is in series with the 4. So I can say this will make those who combine those, but then since they're in series with the 4, I'll add the 4 there. So what will this give us? We have 18 over 9, which is 2. 2 plus 4 is 6. So this gives us 6 ohms here. So I hope you guys are able to do that. I'm doing this a little bit quicker because we've done this. I hope you guys are able to keep track. So these, I can remove these 3, and in place of those, I can now just put that 6 ohms that comes. Okay. And we recall, I think it was Lucky who gave us that last time we were just starting earlier on during the year. When we have two resistors which are equivalent and they are in parallel, their combination is always equals to what? Half of 1. So basically these two combined, we will end up with 3. Okay, so this is where we are now. Now I want to just, okay, I keep doing this very quickly, but I want to see, currently I have combined up to this point. I've combined these and we've seen that the combination has reduced to just 3 ohms. Now at this point, I'll start being careful because I do want to come and get the voltage here. So I'll keep that 3 ohms there so that later on, I'll come and look at it. But in the meantime, we continue since we're going for the total resistance. So I'll copy this circuit because I will need to come and refer to it later on. I'll copy it. As I combine the 1 ohm and the 3 ohms, I'll use a new circuit. So the 1 and the 3 are in series, so I'll just add them. So their combination becomes 4. Lastly, the 2 and the 4 are now parallel, so we can just now say 4 by 2 over 4 plus 2. So when you do this, we have 8 over 6. What is 8 over 6? That's 1.33. Okay, so let's keep it like this. So this becomes the equivalent resistance. Okay, so that was the last one. Yes. So having found the equivalent resistance, Now, the second part is saying find Vx. So how do we find Vx here? Well, to find Vx, we are actually going to use this part, because where's Vx? Vx is the voltage drop across that 1 ohm. In as much as we can use the circuit the way it is like that, it becomes a little bit tricky. So in as much as we can use that 1 ohm there, as in the circuit in this form, I'll choose to use this part where everything else other than the 1 ohm has been combined. So those are going to be combined, and remember that combination gave us 3 ohms. So that the 1 ohm whose voltage drop we want to figure out remains visible, because I just want the voltage drop due to that 1 ohm. Now, how do we get that? Well, the 1 ohm is here. This is where Vx is. So here I have plus and minus here. I want to find what that voltage drop is. But before I get the voltage drop there, I want to understand the current that will be going towards the 1 ohm here. Because if I know the current going towards the 1 ohm, I'll just multiply the current times the resistance, and I'll now know how much current is passing there. So you see, it's going to be quite straightforward if I can just find the current going through that 1 ohm. To figure out the current going through the 1 ohm, I'll use this part where they are actually combined, the 1 ohm and the 3 ohms. So when the 1 ohm and the 3 ohms were combined, we get this circuit where the total resistance in that branch where the 1 ohm is, we had the 4 ohms. So I'll use this circuit to now figure out what the current in this branch is going to be. Because the 1 ohm and the 3 are in series, we know to say the current the will experience is the same. So doing this is actually fine. So I want to find the current. I'll label this as Ix, which will be the current passing through the 1 ohm. We know to say, since these are in parallel, we can easily use current division. So by current division, Ix will be equal to, do you guys remember current division? Can someone tell me? Ix will be equal to what here?
Source. The current source. Ix.
Current source, yeah.
Times the opposite distance over the total.
The opposite. What do you mean by opposite? What would be the one you're calling opposite here?
So since we're finding the one by Ix there, so it will be over the total, which is by 2 plus 1.
I think he has mixed them up there.
To be 2.
Yeah.
4 plus.
So when you're using current division, yes, just as Sumila has pointed out there, if you're getting the current passing through the 4 ohms, then it has to be the other. I think that's what you meant when you said opposite. So it's the other resistor, which in this case is the 2 ohms, divided by the sum, which is 2 plus 4. And then multiplying the supplied current, the current they are sharing. In this case, the current they are sharing is the 6 amps, which is coming this side. So this becomes 2 over 6, multiplying 6. And this just becomes 2 amps. So Ix, the current going towards the 4 ohms, is actually just 2 amps. What does this translate into? See, the 4 ohms is a combination of 1 and 3, but these are in series. They see the same current. All we're saying is, at this junction, the current that will split to take this route will be 2 amps. The 2 amps will pass through 1 ohm. The same 2 amps will also pass through 3 ohms since they are in series. Not really interested in the 3 ohms for now. We're only interested in that Vx. So to find Vx, by Ohm's law, it's the current passing through Vx, which is 2 amps in this case, multiplying the resistance there, which is 1 ohm. So this becomes 2 by 1, which is just 2 volts. So we have found Vx. Now, how about the last part? The last part is the power absorbed by the 2 ohm resistor. Where is the 2 ohm resistor? It's this one here. But before we go to power absorbed by the 2 ohm resistor, do we have a question on the previous one? Okay, so looks like we are okay with this one. Well, to get power in a circuit, we use voltage times current. Voltage times current. Another expression that you can use to get power is if you substitute what voltage is from Ohm's law, current times resistance. If you use current times resistance there, you should see current divider. Okay, so someone wants us to repeat current division before we go to power. Let's do that. Okay, so there are two things that you need to get: current division and voltage division. It's easy to confuse the two. So let me quickly run you guys through the two. So if you're looking at current division, how does it work? Well, firstly, current division works for resistors in parallel. So I'll use this to mean parallel. So it only works for resistors that are in parallel. Why? Because when resistors are in series, the current they see will be the same, or the current that passes through them will basically be the same. But when resistors are in parallel, they will share. Now, how does it work? I'll do it for two resistors here. Even if you had more resistors, the idea is that you can combine everything else into just one. So suppose you have current that is coming through using this branch, and let's say this is IS. So this is current that is coming, it reaches this branch, and then it splits. Part of the current comes in this way. Part of the current takes this route. We'll say this is R1 here, and we'll take this to be R2. So let's say this is what you have. Now, let's say you have two currents here. One current takes this route. We'll label this as I3. And the other current comes this side. We'll take this, why am I saying 3? You can say 2. And you can say this is I1. That is IS, supplied current. Okay, how does current division work? Well, if you wanted to find current I2, they are sharing what? They are sharing IS, the current being supplied. So you will be multiplying with IS, but I'll put that at the very end. But it starts with the ratio of the resistors. If you're getting the current going towards the resistor 2, it will be the other resistor on top, R1. Then R1 will be divided by the sum of R1 plus R2. Then this will multiply the current they are sharing, IS. This is how current division works. It's the other resistor over the sum of the resistors. So if it's the current going towards R2, it has to be like this. In the same way, if I wanted to find the current going towards the first resistor, it will have to be the other resistor. Since I'm going towards the first, the resistor that will be on top will be the other, which is the second. And then this will be R1 plus R2. Then multiplying the supplied current, or the current they are sharing. I hope this is okay. To demonstrate this one more time, we'll actually need this current later on. Let's say we wanted to figure out the current that goes towards the 2 ohm resistor. Remember, for power, we'll be doing it for the 2 ohms. So let's say we wanted to figure out the current that goes towards the 2 ohms here. Of course, we will be using this version where we have combined the other into 4 ohms, but now we want to figure out the current that passes through that 2 ohms. Okay, so just a minute. So if I wanted to figure out the current going towards the 2 ohm resistor by current division again, since now I want the current across the 2, I'll say I2 there. It will have to be the other resistor, meaning it is now the 4 ohms on top, divided by their sum, 4 plus 2. Then multiplying the current they are sharing. And in this case, since this is a current source, they are sharing 6 amps. Had it been a voltage source, I would have been forced to use the total resistance to figure out the current being supplied by that voltage source, if it were a voltage source. So in this case, this will just be 4/6 multiplying 6, which will be equals to 4 amps. So this is the current that goes towards the 2 ohms. But I want you to also observe one thing. If you have a junction here and 2 amps goes this side, the supplied current is 6 amps. You want to know the current that goes down. By Kirchhoff's current law, we know to say the current entering is 6, the current leaving we have 2, then we also have this I2 also leaving here. This has to be equals to 0. You have to see that in this case, so these two are leaving. Okay, this goes this side. You have to see that in the end, the current I2 will actually just be the supplied current minus the other current which went towards that 2 ohms. This will also give you 4 amps, meaning that if the 2 resistors are sharing, like the way we had here, if 2 resistors here are sharing that IS, if you can find I2, there is no need for you to use the current division to find I1. Just subtract I2 from the supplied one. The rest will be what was passing there. What does that imply? We did the math here and found IX as 2 amps. Subtract 2 amps from what is supplied. The rest went towards 2 ohms, which is 4. And we saw, even using the current division, we still got 4 amps. So this is current division. Are we okay here? Okay, so I wanted to also describe voltage division, but I'm seeing this is quite long. So I'll share a link for voltage division where this was recorded already, so you just see how it works. But let's finish up this and let's see that power absorbed. For power absorbed, as I was pointing out, all we need is, we have 2 formulas. Power is voltage times current, but by Ohm's law, voltage is current times resistance, meaning that we can still see this as voltage, current times resistance from that V, and then multiplying the current here. But this just implies that we have current squared times resistance. This is still the same as that. Well, this simplifies our life. What do I mean? Using the current division, we saw to say that the current that will be going towards the 2 ohms will be 4 amps. And the 2 ohms, the resistance there is just 2 ohms, implying that we can easily get the power there as the current squared, 4 squared, multiplying the resistance, which is 2. 4 squared is 16. 16 by 2 is 32. So the power absorbed by the 2 ohms becomes 32 watts. And we're done. Any questions there? Another method you could have used to figure out the same thing is to get the voltage, but that would be a little bit longer. And as a student, you want to find the easiest and laziest way to actually work out this question.